Ganpathy will now give his second lecture, and it will be for an hour and 15 minutes, and there'll be 15 minutes for questions.
All right, very good. So let's begin. Let me ask you that question that I said that I would ask you yesterday. How many of you have actually done the homework? You've actually done it. How many of the homework problems did you guys do? 2. How many problems were there? I don't remember myself. But anyway, we'll figure it out. Okay, good. At least some, non-trivial fraction has done something. Okay, that's good. All right, so again, this evening, we're going to have a tutorial. Professor Carr is going to do it first because he wasn't there yesterday. So whatever questions you have, he will deal with. And then after that, I will also be here. All right, so this particular lecture is going to be about the fractional quantum Hall effect. And we're going to do it 2 different ways. Now, fortunately for me, Ajit Balram spoke yesterday afternoon, and he already gave a lightning introduction to the fractional quantum Hall effect and the various kinds of states that you can see. And so my job is made a little bit simpler. So we will first talk about the FQH from the wave function point of view, because also historically, this was the first successful approach to the fractional quantum Hall effect. And here there are, of course, 2 important contributions. There were many important contributions, but the 2 that really stand out and made a huge impact are Laughlin and Gen. And so we'll talk about the Laughlin wave function in some level of detail, and then we'll talk about the Gen wave functions as a whole class of wave functions. Laughlin, of course, is also a class, but it's a very special class, 1 over odd integer. But these guys, the Gen wave functions are much broader. Okay, then we will talk very little about things. There are other possibilities such as the Moore-Reed state, and so on. But I will not say much about them because they're non-abelian. So Eduardo told me my job was to stick to abelian things. I'm going to stick to abelian things. He's going to deal with all the non-abelian things. Yeah, we shared in the telling. So, okay. So then we're going to turn to something else, a different way of thinking about it from a field theoretical point of view. And this is called, Chern-Simons theory. So this goes by the name of Chern-Simons flux attachment, and it's a very important idea. It started in the quantum Hall effect, but now actually it's applied more broadly in other subfields of condensed matter physics. And so it's an idea well worth learning. Okay, and in fact, this idea was already there in the picture of Jan, but then the first person to really do it in some field theoretic way in the fermionic case was Eduardo. There were some previous attempts in the bosonic case by people like Gerwin MacDonald. They had some idea. It was more concretely realized by Shucheng Zhang, Hans Hansen, and Steve Kivelson. And that was a composite boson thing, but that again applied only to the Laughlin fractions. Okay, and to address the principal fractions or the Jan fractions, you need the fermionic theory that was developed first by Ana Lopez and Eduardo sitting here. So he will, at some point, I'm going to get tired, and I'm going to start making mistakes, and then Eduardo, having infinite energy, will jump up, and I will sit down in his place, and he will take over. Okay, very good. So we're going to do Chern-Simons flux attachment, and we're going to do it from the Lopez-Fratkin point of view. And I'm going to end with this famous paper. I'm going to just give you some journalistic impressions. It's like the headlines that people report when some big event happens. I'm not going to be able to go into any of the details of this. There was a beautiful paper by Halperin, Lee, and Reed. And this is about the very special state at nu plus a half, which is a composite fermion Fermi liquid. Okay, so that will be the plan of today's lecture. And once again, ask me lots of questions, interrupt me at any time, but please use the mic when you're asking a question, because otherwise it will not be recorded. Okay, So let's talk about the fractional quantum Hall effect. As Ajit already told us, he showed us that picture, which I'm not able to draw, but there is a plateau in the Hall conductivity at basically 3h over e squared. Okay, and so this cannot be explained by any integer filling of a Landau level. The integer fillings are basically, so this is not integer, definitely not an integer quantum Hall state. Okay, there is a plateau here. In fact, it's a very robust plateau, and it appears to be as strong as any of the integer plateaus. Okay? Remember, the integer quantum Hall idea was basically RH, n was h over n e squared, okay, where n is an integer. How do you understand this? The simplest way of understanding it is that you think about all these edge modes. So there are n Landau levels filled, they have n edge modes. Each edge mode has a conductance of e squared over h. Conductance and resistance are opposite. So the resistances add in parallel. Okay, and that is why it's h over n e squared. So that's the integer. Okay. Now, so this guy 3h over e squared is definitely not me. So what is it? There were many ideas. Most of them were wrong. Laughlin got the first right idea. So in order to describe the Laughlin wave function, I want to first talk about something known as symmetric gauge. So in our previous lecture, last lecture, we used a particular gauge called Landau gauge, and that gauge had the field, only one component of the field was non-zero. Okay? So here's Landau gauge. And in Landau gauge, A is simply minus Bx Ey, right? And of course, for convenience, I'm going to use minus Bez. Okay. And this was the case for Landau gauge. And now we're going to use something called symmetric gauge. And this turns out to be a very convenient way to write down wave functions in the lowest Landau level, because other than some Gaussian factor, it turns out that these wave functions are all analytic functions. It's a very convenient gauge to express these functions. So symmetric gauge, we have a different gauge. Of course, it has to give you the same magnetic field. So it must be y Ex minus x Ey. Okay. And now, if you've read the first set of notes, there's a way of decomposing all these coordinates and momenta and so on into two sets. Okay, I don't know if you guys went through the notes. So let me just give you a lightning review of what is there in the notes. It's actually in the first set of notes. So basically, you have these operators, which I'm going to call pi. Okay, so pi is operator P plus E times A of X, right? These are called your velocity operators, but strictly speaking, they should be divided by m to call them velocity operators. But let's call these guys the mechanical momentum operators. Okay? Yeah. E by definition is 1.6 times 10 to the minus 19 coulombs with a plus sign. So that is why I'm writing as P plus EA, because the charge of the electron is minus. And that's also the reason why I chose this, so as to cancel that troublesome negative sign. Okay, so this is the mechanical momentum. And if you take the commutator of this mechanical momentum, Px and Py, okay, you can easily do it. P is minus I h bar grad, right, in quantum mechanics. And so you apply it and you find minus I h bar. There's of course an E, and then this Px will act on Ay and Py will act on Ax, and they'll come with a minus sign. And of course, you will have your curl of A. And again, this minus sign, taking that minus sign into account, you get basically E h bar B. Okay. You can also write this as, I h bar squared over L squared. Let me remind you that L squared is h bar over EB. Good. No. Little p is the canonical momentum. Yeah, you're right. Little p is the canonical momentum. Pi is the mechanical momentum. Absolutely. Okay. Good. So now what you do, the z component of what? The z component. Yes. 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 Thank you. Okay. When I make mistakes, please correct me. Okay. No matter how trivial the mistake is. So. Sorry, what is z going to mean? Yeah. So, good. All right. So let's define. Yeah. This algebra is explicitly gauge invariant. You can see it. It depends only on B. Right? So the algebra is definitely gauge invariant. The operators themselves may not be gauge invariant. The algebra is. Okay. That's good. Yes. Yes. Okay. So now what I'm going to do is I'm going to define a coordinate, which I'm going to call the cyclotron coordinate. Okay, I'm going to define eta as a cyclotron coordinate, and I'm going to define it as L squared over h bar times z hat cross. Okay, let me make Eduardo happy by saying Ez cross pi. Okay, and what this means is that eta x should be equal to minus L squared over h bar pi y, and eta y is L squared over h bar pi x. Okay, you can write this in some compact way by saying that eta I is minus epsilon ij pi j L squared over h bar. Okay. So now if you take the commutator of eta x and eta y, you will find IL squared. Okay, I invite you to go home and do this, or maybe even just do it in your head and verify for yourself that this is correct. Okay, so the point of multiplying all these L squares and so on is that it makes eta of dimension length. Okay, eta has dimension length. All right. Now, of course, this is all just pi, right? But there are also the two other coordinates sitting there, which are x and y, right? So what I'm going to do now is I'm going to say that my R, okay, is going to be divided up into eta and something else. And this capital R is what I'm going to call the guiding center operators. Okay. And again, this R, of course, does not commute with the eta, right? Because the eta has some pi sitting in there. But again, I'm not going to go through the details. They're all spelled out in the notes. And again, I invite you to go home and do it yourself without even looking at the notes. You will find the following amazing set of commutators. You do Rx and Ry, you find minus IL squared. And finally, you do R, let's say alpha and eta beta, you will find 0. So this set of guiding center operators commutes with the set of cyclotron operators. It's a different way of rewriting, x and p. So there were, x, y, px, py. There were 4 of these operators. I've divided them up into a different set of 4, such that 2 of them have this kind of phase space commutator, right? Because when something commutator something else is a constant, you immediately think of x and p. So you can think of one of them as x and the other one as p. And there are 2 sets such of that type. One of them is a cyclotron set. The other one is the guiding center set. Yeah. This little r means x, the x plus y py. Okay, so it's just the position coordinate of the electron.
Actually did not understand what's the motivation of writing eta vector.
Right. So it turns out, so now it's coming. Okay, so it's coming. So you can write the Hamiltonian. So remember what the Hamiltonian was. It was simply, pi x squared plus pi y squared over 2m, right? So you can rewrite it in terms of eta. You can write it as h bar squared over 2m L squared eta squared. Okay, so the Hamiltonian depends only on eta. Now, the nice thing about this kind of separation is that both of these r coordinates, rx and ry, commute with the Hamiltonian. Okay, so previously we had identified ky, right, py as commuting with the Hamiltonian, but now we see that both these r's commute with it. So r alpha with the Hamiltonian is 0. So you should be able to simultaneously diagonalize rx and ry and the Hamiltonian, right? How many people say yes? Yes, you should be able to simultaneously diagonalize rx, ry, and h, right? Yes, raise your hands if you say yes. You should be suspicious. Okay, I often trick people like this. Of course, you can't because Rx commutes with H, Ry commutes with H, but Rx and Ry don't commute. So you can't simultaneously diagonalize all of them. So you can diagonalize one of Rx and Ry and then use it as some quantum number and then also diagonalize it. And that's what we did last time. Okay, in that particular gauge, Py was some multiple of one of the R's. Okay. All right, now that we have this, what we can do is we can look at the lowest Landau level. So, or any Landau level. Yeah. Do you have the mic? Yeah.
Is the expression of R there, capital R? There
What
is,
the expression of R?
I mean, the small r is the usual.
X is x minus eta x. What is eta x? This is x minus L squared over h bar pi y. And what is it? Now this depends upon the particular gauge. So let's work it in symmetric gauge. Okay. So this is x plus L squared over h bar, right? And this would be py, and this would be plus e ay. Sorry, I forgot a factor of 2 here. Nobody caught it. Okay. Minus h bar x over 2L squared.
Okay. So this x operator is the xy, the coordinate we started with from the beginning.
Yeah, in quantum mechanics, x, y, px, py are all
operators. Yeah. Understood.
Okay. All right. So that's what it is. And similarly, ry has some similar expression. So this is y minus theta y, and this would be y, and then that would be a minus L squared over h bar, and then this would be a px, right? And then this would be a plus h bar y over 2L squared, right? So basically what it amounts to is that Rx is x over 2 plus L squared over h bar py, and Ry is y over 2 minus L squared over h bar px. Okay, so this is what it boils down to. All right, now the nice thing is that this, because Rx and Ry both commute to the Hamiltonian, the entire degeneracy structure of a Landau level is controlled by these guiding center coordinates, guiding center operators. Okay, and this is another way, a very beautiful way of deriving the degeneracy of a Landau level, is to simply tell yourself that if I'm within a Landau level, the etas are all frozen. Okay, so this Rx and Ry, they can go over this space, which is Lx and Ly, right? Because there are 4 coordinates, but there's a phase space now. So the physical space itself has become like a phase space when it's projected to a Landau level. Okay. Now you know that in phase space, if I have phase space, supposing I have X and P, commutator is IH bar, right? You know that in phase space, you can make little cells. So there are cells of phase space. Whose area is H. Each cell of area H contains 1 quantum state. You guys know this? Okay, approximately, right? So in the same way here, because the role of H bar is being played by L squared. Okay, so from here, you can immediately see that from Rx, Ry is minus IL squared, each cell of 2 pi H bar, which is 2 pi L squared, has 1 state, 1 quantum state. Okay, and that is why the degeneracy of this Landau level is Lx Ly over 2 pi L squared. Okay, that's another way of doing it without ever talking about any particular gauge. Okay, so anyhow, the important thing for us for this symmetric gauge is that now what you can do is you can combine these guys into a set of ladder operators. Okay, you can take things like, for example, you can take, it's either, so let's call them B operators. So it's either Rx plus IRy or Rx minus IRy. I forget which of it is, but you got to divide it by L root 2 to make it properly normalized. And B dagger is, of course, simply B dagger. You take that commutator and then you find, so let's see, which one is it? It's actually the other way around. This should be minus, and you can find easily that B with B dagger is 1. And once you have a set of ladder operators like this, you can construct all the harmonic oscillator states. But these states are now lying inside the Landau level. Okay. So what are these states? So these states I will call M. So these states M are defined as B dagger to the power M acting on the lowest level over square root of M factorial. How is the lowest level defined? Is defined as being annihilated by the destruction operator. Okay, question?
So the last time, like there's in the symmetric gauge, we find like the momentum operator in one direction coming to the Hamiltonian, and you find all the possible value of momentum, and if then find the degeneracy by what lies inside those. So here also we have one operator that commutes with the Hamiltonian.
There are 2 operators that commute to the Hamiltonian,
independent,
but they don't commute with each other.
So can we do something like R commutes with H and find all the eigenvalues of R, then restrict that what are the eigenvalues of R that lies inside? Can we do something?
You can. This is exactly that. I'm going to do that for you right now. Okay. So in other words, this state M is now sitting inside a Landau level. Okay. The quantum number N was the Landau level index. That, the energy depended upon N. The energy does not depend on M. Okay. And in the bulk, and these are the states M. Okay. Now you can ask yourself, okay, this is all very abstract. What do these states M look like when I'm sitting inside, when I want to go in real space? So for that, what you do is you take this B, it's written in terms of these guys. These guys are written in terms of some operators, right? So let's see what these operators look like. So this is Rx minus IRy, right? So there'll be an X minus IY. Okay. You guys see that, right? Rx minus IRy. So there'll be an X minus IY. I'm going to call that Z bar. Okay. An X plus IY, I will call Z. Okay. So therefore, this operator B, I claim, in real space, it looks like 1 over L root 2 Z bar over 2 plus Okay, let me see, L squared D. Okay, what is D? D is simply D by dz. D bar is D by dz bar. So I'm going to switch now from X and Y to X plus Iy and X minus Iy. Okay? And that gives me this expression. So now it's very easy to find out what the state 0 is. So if I want to have 0, so this 0, and I look at X comma Y 0, you just write a differential equation that this operator annihilates that state. And it's very easy to find that state. That state is simply e to the minus z bar over 4L squared, some normalization factor. What is it? 2 pi L squared, something like this. Okay? So that's what the state is. And now I want to create all these M states. So what are these M states? I have to apply B dagger to the M. What is B dagger? Again, I invite you to check it. It's L root 2, and then there's going to be some Z over 2 minus L squared B bar. That is what B dagger is. So you apply that. And the nice thing about this D bar is that when D bar acts upon this, it produces another Z. Okay, because you're thinking of Z and Z bar as independent variables now. So D bar acting on this Gaussian gives you a Z. Okay, so no, there's no I there. Because the minus where? B to B dagger? Just look at the expressions for Rx and Ry. They're not exactly symmetric. There's some minus signs there. I'm not following your question. You're saying why are these like this? Yeah. Z over 2L squared minus Z over 2L squared. Right? I'm sorry. I think there's a minus. I think I messed up the. No, this is correct. What's wrong with it? No, this is correct. Relative sign right here. It's all good. It's correct. Okay, relative sign is correct. Okay, just work it out. Okay, so the point is that this D bar acting on the Gaussian will also give you a Z. Okay, so eventually what you find is that this X, Y on this M state, so this is the punchline now, is Z to the M with some normalization factors. Okay, so there's some L to the M, there's some 2 to the M factorial, and then there's this Gaussian factor. Okay, that is the punchline. So the bottom line is that in the lowest Landau level, all these wave functions that are sitting inside, all the one body wave functions are all analytic functions in the symmetric case. And that makes life really, really simple. Now we are able to write down the Laughlin wave function, which Ajit already wrote down yesterday, but let me write it down again. Okay. So Laughlin, analytic, this part of it is analytic. Yeah, the Gaussian factor is always ignored because it comes attached to every wave function in the lowest Landau level. So therefore you don't care about that. Okay, that's just, and the analytic part is the other part. Okay, other questions? So I spent way more time on this than I thought I would, but anyway, let's proceed. So now what Laughlin wrote down is he said, here's a wave function for 1/3. So let me call it psi sub L or psi sub 1/3. Okay, and it's of course a many body wave function. And what is this? So there's a Gaussian factor, but other than the Gaussian factor, it is simply Zi minus Zj cubed for all pairs.
Question.
Times the Gaussian factor. Yeah.
If I understood correctly, then this B and B dagger is actually moving inside inner Landau level,
Yeah.
fixed inner Landau level.
Yeah.
It's moving from one degenerate state to another degenerate state, right?
That's correct.
So can I get a feeling that what's the number of degeneracy? I mean, there should be some B dagger to the power M, where M is the degeneracy.
Yeah.
And that will give me the 0.
Yeah.
So can I get the
You will
value
see
of
it
the
very
same?
shortly.
Okay.
You will see it very shortly.
Okay.
Okay.
Yes.
Yes. You'll absolutely see it. Okay. So there's the Gaussian factor. And now, the first claim is, of course,
I have
that-
another question.
Yeah.
I actually want to have one clarification. The Z bar you have taken.
Yeah.
That is same as X minus IY, right?
Correct.
Okay. Okay. Thanks.
Other questions? Okay, I think what I'm going to have to do is I'm going to take part of the tutorial as actually doing Lopez-Fratkin, because I can see that this is going way slower than I thought. But it doesn't matter. Okay, better to go slow and for you guys to understand everything than to just rush and you don't get anything out of it. Okay, so do stop me with questions. Okay, let's take it easy and do it properly. Okay, great. So the first claim is that the filling factor here is 1/3. How do we know that? Okay, to know that, let's put some limit on the number of electrons. So what I claim they will do is it will fill some particular disk. Okay, there'll be some disk, there'll be some highest value of M, which goes to the question that was just asked. So what is the highest value of M that can be found here? So let's expand this out and take a particular coordinate Z1, let us say. Okay, the maximum power of Z1 is what? Well, every other coordinate, it comes with a Z1 cubed, right? Z1 minus Z2 cubed, Z1 minus Z3 cubed, and so on. So this must be 3 times NE minus 1, right? So this is the maximum value of M. Since NE is very large, I'll forget about the minus 3. Okay, good. Now, what is the size of an orbit which has the value M, the quantum number M? Let's ask that question. You know what this guy is, right? So basically, you can ask yourself, what is R squared in the state M? And you can easily see there's D2R, R squared psi M squared. Okay, do it out. This is just some Gaussian integral that you can all do. And you will find that this looks like 2mL squared. So the value of R sub M, so let's call it the average radius of this guy, is the square root of that, right? So it's L times the square root of 2m. Okay, are you guys following me? These wave functions are basically, they're radially symmetric in their density. Okay, they have some angular momentum because this is z to the m, so there's an e to the I m theta. Okay, so they're varying along. They have definite angular momentum because you're working in polar coordinates, right? So angular momentum is a good quantum number, but they expand and then they have a peak there and then they decay again. Okay, radially. All right. Now there's some place where they peak, and that place is what I'm identifying as the radius of that particular m. Yeah.
What is that psi m?
Psi m is this
Oh, okay.
wave function. Yeah.
This is very consistent with what we did last time. How do we
Yeah.
in the Landau picture the area
Mhm.
between two consecutive lines to correspond to a one
Correct. That is the same thing here. That's the same thing here. So what Yuval is saying, in case people didn't get it, is that these guys, because of the square root here, it actually, they become more and more closely spaced. So as you go out, it becomes closer and closer space because of the square root. And the point is that the area between two successive values of these R, right, is exactly 2 pi L squared. Because if I take I times R bar M plus 1 squared minus R bar M squared, I'll find exactly 2 pi L squared. Okay, That's what Yuval is pointing out.
I didn't follow from where this M max came.
What M? Is
M max equals 3
M max. Okay. So this is my wave function, right? There are n sub e electrons. What is the maximum power of any particular Z? Let's say Z1. What's the maximum power? Well, there's a Z1 minus Z2 cubed, Z1 minus Z3 cubed, and there are n minus 1 such terms. So the maximum power is 3 times NE minus 1. Okay, and that will be true for any Z, right? Z1, Z2, Z3, they're all the same, right? So therefore, the maximum orbit that is occupied is this. So you think of this as a droplet, and there's an edge to the droplet, right? Beyond that maximum value of M, there's nothing. There are no electrons. Okay. So now this is the value. So now what is the area of this droplet? The area of the droplet is pi times R bar max squared, right? R bar max is, what is it? Pi. R bar max is L square root of 6 NE squared. Okay. Let me write it as 2 pi L squared times 3 NE. So the area in these units of 2 pi L squared is 3 times the number of electrons. So the number of flux quanta is going to be equal to 3 NE, and that is what tells you that mu is 1/3. Okay. Yes, question, Serge. Can you take the microphone?
When you wrote down this Laughlin wave function, did you assume that the wave functions on the left, that these were a basis for any analytic function?
Yes. So the point is that all these, so these wave functions are completely in the lowest Landau level. Okay. So it must be some linear combination of products of single particle states in the lowest Landau level. Okay. So this is a very special combination of all those single particle states, products of single particle states.
But is any analytic function a legitimate?
It has to be analytic. It has to be anti-symmetric under the exchange of any pair of particles, and then it'll be legitimate. Okay. And this satisfies both those properties. It also has the property that its filling is 1/3, which is where this plateau was seen. And it has some other very beautiful properties. Okay. Other questions about the definition of the wave function? Microphone.
I understand this M we take, these are the degenerate states for a particular Landau level, right?
Yeah.
So what is the physical significance of this M? I mean, what is this quantum number signifies?
So now we are working in something called symmetric gauge. So we are assuming that the boundary conditions are circularly symmetric. Okay. So that is why we have these kinds of orbits. So imagine that now you put some potential, you make it into a circularly symmetric bowl, then this would be the most convenient gauge in which to quantize your system.
So it's a mathematical.
It depends on your boundary conditions. So you can always do any problem in any gauge, but it will be very hard for you. So you could try to solve a circularly symmetric problem in Landau gauge. You could do it.
Right.
But it's going to be incredibly hard because the boundary conditions will be very difficult to impose.
And is it
So you have
related
to
to
adopt your gauge to the correct boundary.
Is it related to the angular momentum of the?
Yeah, it is. It is.
It
This is
is.
exactly the angular momentum. Yeah. Yes.
Yeah. So
This doesn't work.
it is not working.
Yeah.
So this, so I didn't understand that what area did you calculate, and from that area,
So
how
Yuval
did you?
pointed out that the area between two. So remember that the area occupied by a single quantum state is 2 pi L squared. Why? Because of that reason over there. So Rx and Ry act like a phase space.
Right.
The role of H bar is being played by L squared.
Okay.
So area of H, which is 2 pi H bar,
Mhm.
has one state. But H bar here is L squared.
Right.
So that's why 2 pi L squared should have one quantum state.
Okay.
Now, if you look at the area between successive M orbits, right? then each time they get slightly closer, but then the area between those two is always 2 pi L squared. That's how it's arranged.
Okay.
And just verify.
Okay. So you are calculating that for a M max, how many quantum state would be there and
Correct.
okay.
Exactly. So for M max, there are this many. This is M max, right? So there are this many allowed quantum states.
Right.
That means there are this many allowed quanta, flux quanta, right? Okay, but how many electrons are there? Just n sub e. So the filling is 1/3. Okay, because the filling is always defined as the number of electrons divided by the number of flux quanta.
So that you could read from the M max expression, right? Why did you have to calculate the area here?
Why did I have to calculate the area?
Yeah.
Because I wanted to show it to you explicitly. I didn't have to. I didn't have to. Yeah.
Function that you wrote for Laughlin wave function,
Yes.
the power is 3, right? Zi minus Zj to the power
Yes.
3. And that is giving us the filling fraction of 1/3.
Correct.
Now, that should be true for any odd value also, right?
Yes.
Do we see that
Yes.
for every odd value?
Not every odd value, but 1/5 has certainly been seen. Maybe in some samples, 1/7 has been seen. That Ajit can answer that question. Has 1/7 been seen? Yes. 1/7 has been seen, but not 1/9, right? Yeah. So at some point, so as you increase the denominator, the gap decreases. And
Which
and
gap?
the cleanliness of the sample.
Okay.
So these are incompressible states. They have a gap. And so it takes less and less disorder to destroy the state. These are very delicate states. At large values of the denominator, these are very delicate states. It's easy to destroy them with disorder. They're
But
competing with other states as well. Yeah.
But in principle, we can make those states with any fraction, like 1/5, 1/9, 1/13.
Absolutely.
Okay.
Yeah.
Thank you.
Other questions? Yeah. Take the mic, take the mic, take the mic.
Of electrons are uniform throughout?
If M is large enough, if
Yeah.
M max is large enough, they'll be very uniform in the center. But if you take this wave function, you will find that there's some other stuff that happens. But in the center, there's a large area which is uniform. Within a few magnetic lengths of the edge, there'll be some non-uniformity.
Because over the circle, of course, the circle getting bigger, each state can only occupy by a single electron, so the density is kind of going down on the circle as the circle gets bigger, but somehow also the area is shrinking, so they conspire in such a fashion that the physical density remains a constant.
Yeah, the density is always the same.
This
Absolutely.
is just uniform.
In fact, the wave functions are more and more spread out. Okay, their width gets bigger because of this z to the m, right? The bigger the m, the bigger the width of this wave function.
It just makes it
Yeah.
uniform. Yeah, okay, thank you.
Okay, any other questions? Yeah.
Actually, I have to go back to that equation, that wave function. So let's consider the wave function to be with the power 1, which is the integer part.
Yeah.
So in that case, the NE will be equal to Mx, which
Correct.
makes sense to me.
Yes.
But when you put power 3, it goes 3 into NE. But I think the NE is the number of electrons filled in a particular Landau level.
This is the number of electrons in this droplet.
Yeah, that should
It's
be.
all in the same Landau level.
Yeah. So that should be actually the number of filled Landau levels, means those are the states in a particular Landau level, right? Those are the
It's
available.
all in the same Landau level. It's the lowest Landau level.
Yeah, those
So
are the available states in the lowest Landau level.
There are many more states available, but this droplet is filling only that area.
So basically, when the power increases from 1, the number of states available for the electron just increases from, let's say, NE to 3NE.
Okay, so let's imagine the following scenario. Okay, so let's imagine that I have a finite disk. Okay, and then there's some edge boundary condition that I don't care about. Okay, so the total number of available states, single particle states, is 3 times NE. Okay, and now I try to ask how many possible ways can I fill NE electrons in 3 NE states? Enormous number of states, right? Something like, these are all spin polarized electrons and they're fermions. So it would be something like, 3ne factorial over ne factorial 2ne factorial, right? Something like this is the number of possible one particle states that I can construct, many body states, right? So the true ground state is some linear combination of all of these guys, some really, really gigantic number because of the factorials. But now somehow nature chooses that particular state, which can be written that simply over there. Okay, that's sort of miraculous. Okay, and Laughlin guessed it. Right? Other questions?
Hello.
Yeah.
Yeah. So I do understand that there should be a odd power when you are writing the wave function.
Yeah.
But how does it make sense? Like, why should we not expect nu equals half, let's say?
Why should we not expect nu equals a half
Huh.
here?
Yeah.
But if it's a even
Yeah, I
power,
do understand it should be antisymmetric.
Yeah.
But like physically speaking, why should not half of the Landau states be filled and just some odd fraction should be filled?
there are states which are half filled, which are also incompressible, like the 5/2 state that Ajit talked about yesterday. It's like this. It's got a square there,
Okay.
but it's got some other antisymmetrizing thing which doesn't affect the filling.
Okay. So there
That's called
can
the
be
partial
half
state.
filled.
There can be half
Okay.
filled and still be incompressible. Yeah, that can happen.
Okay. Thank you.
Okay, and there are lots of other. So he talked about Gen fractions, which we're also going to talk about. And they're not half or 1/3 or any 1 over anything. They're 2/5, 3/7, and so on. So you can have many incompressible fractions. Doesn't have to be 1 over an integer. Okay. So anyway, all these things go to 1. There's just a single state, and it's that Laughlin state. Okay. So now let's ask ourselves, what are the properties of this Laughlin state? So first of all, Laughlin found that it's a liquid. Okay, what do I mean it's a liquid? I mean that it doesn't break translation symmetry or rotation symmetry in the thermodynamic limit. Okay, how did he find it? Well, there's some complicated numerics that you have to do. You can actually find the the pair correlation function. Okay, that you can do by some pretty complicated numerics. Okay, so you do that and you find the pair correlation function and you find that it's completely radial, it's circularly symmetric, and it has no hint of translation symmetry break. So it's a liquid. Okay. The second point is that it's incompressible. Okay. This is the thing for interacting systems that plays the role of a hard gap that exists between Landau levels in the non-interacting system. Okay. This is what actually ensures that there's a quantization of the Hall conductance in the presence of disorder. So the state has to be incompressible, which means that if you want to make a charged excitation on top of the state, it takes a finite amount of energy. You can't make it at an arbitrarily low amount of energy in the bulk. Okay, that's what incompressibility. Third, he showed that the excitations, the lowest energy excitations are fractionally charged. They are this. Okay. So this is actually pretty easy to see. So let me show this to you. And the way it works is you say, what is the simplest excitation I can think of? Well, I already have this Laughlin wave function. I want to multiply it by some other function of z. This guy is already antisymmetric, right? Between the exchange of any pair of particles. So I have to multiply it by a symmetric function of z in order to preserve the antisymmetry of the complete wave function. So Laughlin said, I'm going to make something that he calls a quasi-hole excitation. It's simply going to be, this guy is going to be sitting at a point z0, this quasi-hole, and it's going to be this. This is whatever that was. Okay, it's the good old wave function, Laughlin wave function, but you multiply it by this factor, which is symmetric in all the z's, so the entire thing is still antisymmetric. It's a good wave function. Now, what does this do? It pushes the particles away from Z0, right? It reduces the density near Z0 to 0. If you actually calculate the charge of this, there's a very beautiful way to calculate it. which I have given you as a homework, which is you put a solenoid at Z0 and you slowly, adiabatically increase the flux through the solenoid until it's one flux quantum. Okay. Why is this one flux quantum? Because if it's one flux quantum, then the electron, when it goes around it, it acquires a phase of 2 pi. We talked about that yesterday, right? And this is exactly that 2 pi that it goes around. So that is why this is the correct thing for inserting one flux quantum adiabatically. If you use the fact that this state has a Hall conductance of 1/3, then you can easily show that when you adiabatically insert a flux, you push away a charge of E/3. Okay, so go and do that at home. It's a very useful exercise. Sorry? The energy is unchanged. No. The energy is changed. The energy is changed. This is an excited state. The energy of this state is not the same as. Yes. So the point is that, so in order to do all this properly, you have to ask what happened to that charge, right? So you take this guy, the state here, and you calculate the energy of the state in the Coulomb interaction. There's no kinetic energy, but there is a Coulomb energy. So the initial state was uniform. This state now has a charge inhomogeneity. This 1/3 charge that disappeared from this place Z0 has now gone to the edge. There's now a charge inhomogeneity, and that will cost you some energy. And Laughlin actually calculated that energy by some other numerical method. Okay? So in fact, it's a finite energy excitation. All the energy scales, are proportional to E²/L, which is the scale of the Coulomb interaction. So everything's controlled by the Coulomb interaction. Okay, the kinetic energy is completely degenerate, it doesn't play any role in any of this physics. Okay, good. So you got incompressible state with fractionally charged excitation. And then beyond that, a couple of years later, or maybe the same year, I forget what it is, maybe next year, Arova, Schrieffer, Wilczek also showed that if you take two of these quasi-particles and you exchange them, you get a phase, which is neither +1 nor -1, it's actually e to the I pi/3, okay, upon exchange. Okay, or maybe it's 2 pi/3. 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 Very good. Yes, sure. Question? No question. Sorry. Yeah. Now it's 2 pi/3. Yeah. I was talking about exchange. Exchange is pi/3. Yeah. 2 pi. Yeah. Yes. Yeah. 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 What do you mean by a higher level? What do you mean by a higher level? Higher Landau level? Away. Yeah. Actually, no. There are two contributions to the energy. There's a contribution of just the quasi-particle itself. So let's assume that there's a neutralizing background, which is uniform. So when the guy was a liquid, there was no energy. Right? There was some exchange energy, there's some correlation energy. Okay, but there's no electrostatic energy. Okay, but now you created this quasi-hole, it has an electrostatic energy because it's a charge. It has to have a self-energy, right? It's a distributed charge, it's going to have some energy. And that energy is going to be of order E²/L. There's that energy. There's also the energy at the edge, if you have to climb some potential. At the edge, right. But that energy is associated with the edge, not with the quasi-particle itself. Okay. Other questions? Yes. There's also an extra charge. Yes. Yeah.
So here, this is what Ajit was also pointing out, that this wave function doesn't have any variational parameter.
Yeah.
This is just an
It has no
exact wave
variational
function.
parameters. It has no free parameters. Yes.
Yeah. But this is with the assumption
Yeah.
that it is absolutely radially symmetric all the way through.
It's what?
It is completely radially symmetric even at the boundary. So if you have a hard
Yes.
potential at the boundary,
Yes.
but let's say I think about a slightly different situation where the boundary is not defined by the hard potential.
Yeah.
Then these wave functions can have this boundary can shape differently to reduce energies.
True.
Right? So I
True.
can introduce a variational parameter. In principle, if I let go the idea that only the radially symmetric wave functions.
Yeah, but look, the boundary, so I'm assuming that this n sub e is very large. So whatever happens at the boundary, yeah, it happens at the boundary. It's going to affect some states within a few magnetic lengths of the boundary. But really, it's not going to affect my bulk side. Right. So we're talking about bulk properties, right? Okay. Other questions? Okay. So now let's go on. So this, of course, holds for all 1 over odd incompressible states. And this was a huge achievement. And this was basically, the first crack in the enigma of the fractional quantum Hall effect. So we certainly understood one category of states. But there are many other states. There's this whole so-called principal sequence or the Jane sequence. And that's n over 2n plus 1. Okay, so let's just confine ourselves to this. Okay, so what about these guys? Well, so Jan came up with this brilliant idea of vortex attachment. Okay, so now there's some history to this. Okay, there's some history because there were people who were thinking about flux attachment even before Jan, and there were people like, as I said, like Irvin McDonald, and then Jang Hansen and Kivelson. But in 1989, Jane came up with this brilliant idea that basically unifies many fractions into one framework. And this is known as the composite fermion picture. And of course, it starts as a picture, but there's serious testable consequences. You can write down wave functions, you can calculate energies, you can do many things. Okay. And so what is the CF picture? So the CF picture, there's a brilliant cartoon by Juan Park. It goes something like this. So there's some, let's take the case of 1/3. So there's some fluxes and there's some electrons, and you can see that they're very unhappy, right? Can you see that they're unhappy? Yes, because whenever something is unhappy, you turn the mouth like this. This is a code for saying there's unhappy. Okay, but then what happens is that each electron grabs a pair of flux quanta, and then it becomes happy. Okay, why is it happy? So this was 1/3. The reason it's happy is because each of these composite fermions now, this is a CF, each of these composite fermions has exactly one flux quantum to deal with. And therefore it is at effective filling factor of 1. Okay, so that's the idea. So if I want to write down some elementary, some numerology of this, so what would I say? I would say that there's some n phi, but then each electron captures 2 flux quanta, swallows it somehow. We don't know how exactly yet, but we'll see shortly. So it swallows 2 flux quanta. So the number of flux quanta left is this. Okay, that's n phi effective. So what is nu effective? Nu effective is going to be the number of electrons, which is the same as the number of composite fermions. You can see, right? 1-to-1 correspondence between the number of electrons and number of composite fermions. This divided by n effective, n phi effective. Okay, what is this? This is Ne over n phi minus 2Ne. Let's divide this, let's take the n phi out, and let's say nu effective is Ne over n phi, 1 minus 2 Ne over n phi. which is nu over 1 minus 2 nu. And then I say whenever this nu effective is an integer, then these composite fermions fill an integer number of their own composite fermion lambda levels, or lambda levels, as Jane calls them. And then the state will be naturally incompressible. Whenever some kind of fermion fills an integer number of lambda levels, it's an incompressible state, very natural. Okay. So that says that the value of nu should be nu effective divided by 1 plus 2 nu effective. And then you start filling all the integers that you know about, and you find exactly this chain sequence. So nu equals 1, you get 1/3, nu equals 2, you get 2/5, nu equals 3, you get 3/7, and so on. Okay, so everything works out. Okay, great. So in one fell swoop, Jen has explained all the principal fractions. Okay, so right now you say, okay, this is a picture, it looks very cute and everything, but what's like something more serious than a picture? Okay?
I have a question.
Yeah.
So is there any equivalence between the Laughlin explanation and the composite fermion explanation?
Yeah, there it is.
Okay.
I mean, Laughlin state is one member of the principal sequence.
So 2/5, 3/7 can only be explained by the composite fermion,
Correct.
which Laughlin cannot cover. And how
Well,
do
there are some ways of thinking about 2/5 in terms of the Laughlin state, and then you start putting some quasi-particles on top of the Laughlin state, and then you condense those quasi-particles into their own Laughlin state and so on. So there was a picture called the hierarchy picture, which eventually led to the 2/5 state. It's a very complicated way of thinking about it. Okay, mathematically, eventually they become equivalent, the Jane construction, but this is a much simpler way of thinking about it.
And how do the lambda levels modify with the composite fermion picture?
You mean the electronic lambda levels?
Yes, yes, because we were
This is
dealing with.
all sitting inside the lowest lambda level.
Okay.
All sitting inside so there's no kinetic energy. Somehow the system is generating by itself a set of lambda levels for these composite fermions.
Actually, in one way, my what do I mean? How do the m value we were discussing in the Laughlin wave function? How do the m value changes here? For 1/3, I know m is 3, but for 2/5, is there any such m kind of thing?
There is no particular m. There's no definite m for these states. I'll show you what the wave function looks like. It doesn't look that simple. It is something else. Okay. So Jen said, okay, the way to do it is to think about the psi of the electron. This is now some function of, let's call it Ri. Okay, the positions of all the electrons. This is going to be this factor called the Laughlin-Gastaut factor, Zi minus Zj squared, times some wave function of composite fermions, and this is going to be at nu effective. The coordinates of the composite fermion are the same as the coordinates of the electron. Okay? Now, what does this guy do? This is the guy that does the flux attachment or the vortex attachment here. Okay? There's a phase when the electrons go around each other. There's an extra phase of 4 pi because of that, because of the Zi minus Zj squared. And then there's whatever wave function, which is some integer quantum Hall wave function for the composite fermions. Now, anything except nu effective equals 1 will have Z bar as well as a Z. So if you want to stay within the lowest lambda level, you project it. Correct. Correct. So if you want to describe 1/5, you'll have to attach not 2 flux quanta, but 4 flux quanta for the composite fermions. And there's another principal sequence which comes with 4 flux quanta attached. You can attach any even number of flux quanta and still get fermions. Okay. So yes, 1/5, and then what is it, 2/9 and some other fractions like that can also be described using this picture, but attaching 4 flux quanta. Okay, good. So this is the prescription now. What Jen did was he took these wave functions, he did some exact diagonalization on the sphere, and then he found that the wave functions had beautiful overlap with the exact states. Okay, so this justifies that. And so this picture really has some masala in it, right? I mean, it's not just a picture, it's really like a theory of this, at least for the wave function. Yeah.
Psi CF V effective. So that is, I mean, V effective for V effective is equal to 1. So that is the,
Stage is 1, but
yeah.
the 2/5 stage is 2.
It's 2. But what about the anti-symmetric factor? That was not in the, I mean, when we wrote the, for one Landau level in a symmetric gauge, when we wrote the wave function,
Yeah.
how do we impose the anti-symmetry?
You don't have to impose anything. This wave function, so this part is symmetric, right?
That's right.
Okay. But this part, because it's a one body wave function,
That's right.
it's the Slater determinant. By definition, it has to be anti-symmetric.
Oh, okay, okay.
It's a fermionic wave function.
Yeah, I agree with you.
Definition anti-symmetric. And this is true for any new effective. It's going to be complicated, more and more complicated as new effective increases.
Huh.
It's always anti-symmetric.
Okay.
So this part imposes the anti-symmetry and the composite fermion wave function. This guy attaches the flux and pushes the particles away from each other. Okay, you can see that, right? As the particles approach each other, there's some extra suppression factor, and that is what the Coulomb interaction is doing. That is why the system does this in the first place, because the Coulomb interaction doesn't want the particles to be close to each other. It wants the particles to be far away. This type of wave function makes sure the particles stay far apart. Okay, that's the reason for this, why this thing happens. And that's why would it ever happen? Because of the Coulomb interaction, why it happens.
Another question regarding that when we have integer filling, so we ignore the Coulomb interaction in that case, but the particles between themselves feel the Coulomb interaction, right? So somehow that we ignore it. So why is that?
We don't ignore it. We ignore it as a first step.
Okay.
Take it into account at the next step.
What are
the consequences of the Coulomb interaction?
Okay.
What will happen is that the excitation energies to the next Landau level will get increased when you add the Coulomb interaction.
Okay.
You can also compute some other excited states which are collective modes. Okay, like a particle hole excitation.
Yeah.
Find the eigenstates in the presence of the Coulomb interaction. They will definitely depend on the Coulomb interaction.
Okay.
The state itself is not affected by the Coulomb interaction. The state itself remains the same because it's a completely filled Landau level. There's no room there for doing anything.
Okay.
Good. Right? Other questions? Okay. So this set of wave functions is amazingly successful, not only for the ground state, but you can also now create excited states. Okay, so what's the picture here? The picture is
sorry, I have a question online. So this projection to the lowest Landau level, is it can it be done by hand, or is it has to be done numerically?
the expert on that is sitting in the back row. Okay. I believe there's some very clever trick for doing it on the sphere, which, you can just do it in one shot. Is that correct, Ajit? Yeah, you can do it on the disk also, he says. Okay. There's some extremely clever ways of doing this, which don't involve any huge numerics or anything. If you want to do it brute force, yes, you have to do something very complicated, but there are some tricks that can be used.
Okay.
And you should probably read Jan's book or the papers with various people. Camilla, many people, Park, Ajit Balram himself, and so on and so forth. Okay, I don't know exactly what those tricks are, but they exist.
Great, thank you.
Other questions? All right. So now there are some other things that you can do. So for example, you can do excited states. So what is the picture of excited states? So the way you think about this state now is you say, okay, now there are some lambda levels. So this is the n equals 0 lambda level. This is the n equals 1 lambda level, n equals 2 lambda level, and so on. Okay. And some number of these guys is filled. So let's say you have new effective is 2. So 2 of these lambda levels are full. Okay, that is the ground state. Now you can actually ask yourself, what is the natural sort of excited states I can think of? If you want to think of a charged excitation, you can either add a particle there to the next lambda level, or you can remove a particle from an already filled lambda level. Okay, so these are, so how do you implement that? Well, there are obvious wave functions here, right? So there's a wave function of these two filled lambda levels plus an extra particle. There's such a wave function here, right? Because it's an integer quantum Hall wave function with an extra particle. Just put it in there, multiplied by this Laughlin-Jastrow factor, project, and you get your candidate for that excited state, the charged excited state. Similarly for the hole. You can also do things like particle-hole pairs. Okay, and the amazing thing is that a lot of these low-lying states in the Jane sequence are very well described, as it showed us in a picture yesterday, very well described by these states. Again, with zero adjustable parameters. Okay, so it's an extremely successful theory. And then the last 4 minutes, let me just go to two different things. One of them has to do with nu equals a half. Okay, so nu equals a half, you would say, normally you would just say, I less than j, zi minus zj squared, right? That guy's nu equals a half. The sad part of this is symmetric. It's not anti-symmetric. You want it to be anti-symmetric. In order to make it anti-symmetric, what you do is you multiply this by something that forces the anti-symmetry, but it doesn't actually change the filling factor. So what is this PF? This PF is what's called a Pfaffian. It's the square root of a determinant. So what you do is you take an even number, you take an anti-symmetric matrix. Okay, so let's take some 4x4 anti-symmetric matrix. So let's say this is A12 minus A12, and then there is, I guess, A13 minus A13, A14 minus A14. You get the idea. Okay. Now you take the square root of the determinant of this guy, and you can easily convince yourself this A12 is, let's say, 1 over Z1 minus Z2. If A12 appears, then nothing in this column or this row can appear, right? So therefore, there won't be any other A1s. There won't be any other Z1s. So it won't change the filling factor. Okay, because the filling factor is completely decided by 2 times n electron minus 1, okay, the highest power of Z. So it doesn't change the filling factor, but it makes it anti-symmetric. And there's a perfectly good wave function. This is known as a Moore-Reed wave function. Okay. Then another thing you can do at nu equals a half is actually a little bit simpler conceptually. You ask yourself, at nu equals a half, NE, 2 times NE is exactly equal to N phi. Okay, that's the definition of nu equals a half, right? So what happens there? So what happens there would be, you would say that this wave function psi electron nu equals a half would be basically this Jastrow factor I less than j zi minus zj square times this, Fermi C wave function, composite fermion Fermi C. Okay, and you basically have K states because the composite fermions don't feel any effective magnetic field. Right? They've swallowed all the flux quanta. There are no more flux lines left, flux quanta left. They form a Fermi C, and this is just some determinant. E to the I Ki dot Rj. Right? You fill up all the K states within some Fermi surface, within some Fermi C, and you take that monstrous wave function and project it. Okay? So that is a compressible state in the lowest Landau level. And this state, in fact, it has been seen. The state was first thought of actually in a paper by Halperin, Lee, and Reed, which we're going to talk about in the evening, I hope. And later on, this wave function was also used to, they did exact diagonalization. This was Reed and Rezai, or Rezai and Reed did this calculation where they took this wave function, did the exact diagonalization of nu equals a half on a sphere, they took the overlap and they found excellent. Okay, so these are the two things I want to say about nu equals a half. And then the next thing I want to talk about, which I had hoped to actually do during this lecture itself, is the Chern-Simons flux attachment. And now we are going to transition from wave function to field theory. Okay, and that we will start in the evening. I'm going to I'm going to abuse the tutorial hour for an actual lecture. That means that you have to be here. That's number one. But it also is, there's some positive to it. That means that I won't ask you to do the homework on the board. Okay, there's an upside. Okay, questions? Yeah.
Can you tell us about why this Landau-Jastrow factor actually, I mean, corresponds to field flux attachment, further
Right.
flux attachment?
Because the Laughlin-Jastrow factor means that as the electron is going around the other electron, Zi minus Zj. So let's keep all of them fixed except one of them, right? Let's take Z1 and let's say it's going around Z2. So if the electron had seen a flux, as it went around, it would accumulate a phase, right? If it has one flux quantum, it will accumulate a phase of 2 pi. This is, remember, we went through the argument of the Dirac monopole and the string and so on, right? So one flux quantum means 2 pi. Two flux quantum means 4 pi. And that's exactly what's going on here. So it has attached 2 flux quanta, just looking at the phase as you go around it. It's doing much more than flux attachment. This wave function is not only attaching flux, it's also pushing the particles apart. In fact, this is the primary reason it happens, is because the Coulomb interaction doesn't want them close together. Okay, so there are two things going on. The Coulomb interaction wants them to be far away from each other, but the lowest Landau level forces everything to be analytic. Okay, so in an analytic situation, how do you make the particles go further apart? You have to multiply by Zi minus Zj to some power. That's the reason this happens.
Yeah, actually, I can see that increases the degree of the zero. I mean the polynomial.
Yeah. Another way to think about it is increasing the degree of the polynomial means you increase the size of the droplet. Right? Remember that argument about the M max. And that means it reduces the filling. So this factor does several things at the same time. It reduces the filling, it pushes particles further apart, it keeps them apart, which makes the Coulomb interaction happy. And it changes this nu effective to nu by diluting the particles, pushing them apart. It does all of those things. And it keeps it in the lowest Landau level. Okay.
I have a very much vague question. The Laughlin wave function you were writing, where you are taking odd powers of Z minus Zi minus Zj
Yes.
to make the wave function antisymmetric, spatially antisymmetric.
Yes.
That I understand because to make the Coulomb interaction, Coulomb repulsion minimum.
Yes.
But can there be any way there where like wave function energy can be minimized by kind of super exchange so that spin parts will be antisymmetrized and a spatial part will be symmetrized so that we can get to see half magnetization plateau and
Yeah,
1/4.
there are various types of wave functions. There are these things called the multi-component wave functions, okay, where there are basically you have up spins and down spins, and you can have a wave function that has both up spins and down spins. Now, typically in these quantum Hall systems, you assume that there's SU2 spin symmetry. So that puts some constraints on what your spin can do.
Yeah, so basically
Okay.
this can also happen, right?
Yeah, it can happen. I mean, it can happen but the point is that the super exchange, whatever is causing the super exchange, its strength is very much weaker than the Coulomb interaction.
Yeah,
Coulomb
really I am
interaction is
thinking
very,
about
very strong.
Really I am thinking about let's say electrons have a strong on-site potential.
See, this is the problem. These states are all very heavily overlapping with each other. So you should really think of this as a situation analogous to itinerant electrons, not localized electrons.
I see.
Super exchange type phenomena become very important when the
Localized
electrons are
electrons.
localized and they
Yes,
form
correct.
local moments,
Correct.
spins. And then super exchange becomes important because the on-site energy is very much bigger
Correct.
than the hopping energy.
Yeah.
This case is the opposite.
Yeah. Okay.
Okay, the wave functions are all heavily overlapping and there is no.
Okay. Thank you.
Other question.
I have a question. That I have to go to the initial beginning
Yeah.
of the lecture.
Yeah.
That you wrote that Kate of M. Kate of M is B dagger M by acting on 0 Kate, right?
B dagger to the power of M.
Yeah, B
Yeah.
dagger.
Mhm.
And B dagger is related to your capital Rx and Ry, which are
Yes.
the position operators.
Yes.
So in that way, can we call M to be some, I mean, momentum operator I knew later, but initially it was related to only B and it is related to the position only.
Well,
So-
they are guiding center positions. They have both positions and momenta in them.
Okay.
It is capital Rx and capital Ry.
Oh.
They have both R and P in them.
So M effectively comes as an angular momentum operator,
It's an
angular
angular
momentum.
Yeah.
So it is not related to the position or anything.
Look, everything is related to everything else.
Yeah.
Because these guys don't commute, right?
Yeah.
Normally you think of R, X and Y as commuting with each other.
Hmm.
But when you project to the Landau level, in any particular Landau level, they no longer commute. Okay?
Right.
And so you can't you can't measure X and Y at the same time inside a Landau level. They don't commute. So they form a phase space.
Right.
And so in this phase space, so it's exactly like X and P. Whenever you have this phase space that has X and P, you can always form these ladder operators, X plus IP and X minus IP. And you can construct the structure of the harmonic oscillator states, right? So that is exactly what we did. But in this case, the M value also corresponds to angular momentum.
And another question I have, that in the composite fermion picture, so you wrote about this new effective. I actually did not understand how that came.
Right.
Only new
So-
I understand, but new effective I could.
So what I said, so let's go back here, okay? So everything is here. So each electron has swallowed 2 flux quanta. Number of flux quanta left after the swallowing has happened is the original number of flux quanta minus twice the number of electrons, right? You're with me there? Because every electron swallows 2, so the total number swallowed is 2Ne. Okay. Now, I want to say this resulting particle, which is a composite fermion, it sees this many flux quanta. But the number of these particles, composite fermions, is the same as the number of electrons. So if I want to calculate its filling, it's Ne over N phi effective. I just go through some algebra. And that is the relation between nu effective and mu. I can reverse that, get nu in terms of nu effective. And then the key point is this: what should nu effective be? I want an incompressible state with a natural gap. Right? When I think of fermions, and I say, when would they have a gap? I say, oh, well, I mean, if they're sort of roughly non-interacting, they would have a gap when they fill an integer number of Landau. And that's why I choose nu effective to be an integer. If I choose nu effective to be an integer, I find that nu is the Jan sequence. So it gives a very natural explanation for the entire sequence. There's much more actually. It's not just the sequence, but also the fact that at nu equals a half, you can do these things called focusing experiments. You can ask, is the current, what is taking the current? Is it electrons? Is it composite fermions? And this experiment was done in 1996. Okay, there's a paper. Read the notes. You'll see that there's some actual evidence that there's composite fermions. Yeah.
So to write this wave function in which this electron is attached to a flux, you basically multiply this wave function with Zi minus Zj squared.
Yeah.
But I could do something else, right? I could also multiply this wave function by Zi bar minus Zj bar squared.
Yes,
And
you could.
What would
Yeah.
that mean?
Right. So that means you're actually adding to the flux that's already present in the system. And people do that too. That's called reverse flux attachment. That is also done. And there are some wave functions that come with that as well. It's not in the lowest Landau level, but then if you multiply it by some other phi, you can still project it, right? Yeah. Oh, because it doesn't, it doesn't come into the lowest Landau level.
So I have a basic question. So how does this picture reduce to the integer picture? I mean, so we are getting all these fractions, right? 1 by 3, 2 by 5, or whatever.
Yeah.
So
Yeah.
how are we
But the
getting?
fractional quantum Hall effect of electrons, remember the new effective is an integer. New effective is 1, 2, 3. So it's the integer quantum Hall effect of composite Fermi.
No, I mean, I'm talking about the integer Hall effect of electrons.
Yeah,
So how does this is the integer Hall effect of the composite fermions,
right.
but this picture is not the integer Hall effect of the electrons, right?
That's correct. The electrons are different fermions.
Right.
They have their own integer
So
Hall
this
effect.
picture is not like a special case of this picture is not the integer Hall effect of the electron.
It is a special case. You attach no flux whatsoever
Oh, okay.
to the electron.
Right. Okay.
So you can attach any even number of flux. So 0 is also an even number.
Right. 0. Okay.
So you can do that as well. Okay. Yes. All right. Other questions?
Actually, I
Yeah.
have.
Yeah.
Okay.
I think you should keep the mic permanently.
Okay. Actually, we started with the Landau level.
Yeah.
Now, when we go to the composite fermion, we have the lambda level.
Yes.
So how they are different from each other?
They are very different from each other. So the Landau level spacing is controlled primarily at very large magnetic fields. It's controlled by omega c. There's some contribution from interactions, but it's primarily omega c, right? EB over M. Now, inside a Landau level, M has disappeared because all the kinetic energy is completely degenerate. M has been forgotten. So whatever is setting the scale of this, there's only one thing that can set the scale, and that is this, the Coulomb interaction. So all these scales, these gaps between different lambda levels are completely controlled by the Coulomb interaction. So it's quite different. Okay.
There's one point I wanted to make that.
Yeah.
Do you need any, no, this is not to do with this, but if you're going to give some part of the lecture in the tutorial,
Yeah.
the problem will be it will not be recorded. And if you need any part of it for the next lecture, people who've been seeing it online or are not here will not be able to get it because they also use these lectures as a resource.
So you tell me what you want me to do. What shall we do? There will be nobody here. The audio-visual people will not be here in the evening. So that is why it cannot be recorded.
So how long will it be? How much more time would you need for that extra?
Very long.
No, I was thinking if it's
because
10,
it's
15.
even more, I thought this was the simple stuff.
Yeah.
The other stuff is going to be more complicated.
But is it needed for for your next lecture as well?
I could cut it out. What do you think, Eduardo? Just cut out Lopez-Stratkin.
It depends on what you want to
No,
do
the
next.
next lecture is going to be just Chern-Simon's effective theory, K matrices and stuff like that. You don't need to go through Lopez-Stratkin, right? It's there in the notes. No, of course you will not do it. Yeah, because you have many other things to do. Yeah.
So I'm wondering, what is the suggestion? I can try to find out if it can be recorded, but I'm not.
I doubt it will be
I doubt
recorded
it.
because
It
I don't
cannot.
think people will stay,
Yeah.
you know.
It's very late.
Yeah.
So you speak slowly and people take notes.
I have given them notes.
Yeah, no, this is for the people online as well. Particularly today, a lot of people may not have.
So,
People have the notes.
Okay, fine.
yeah. So no, just do it in the evening.
Okay. If you need, no, if you need to, if any part of it is needed for your next lecture, just do it at the
No,
beginning of
it's
the
not
lecture.
really needed for the next lecture.
That's fine. Thank
But
you.
as Eduardo says, it's the most important part. Okay, so evening, first Professor Carr will do his tutorial. And then after that, we will take over. How late is dinner? How late is it open?
I don't know.
10, 11?
No,
Midnight.
We won't go on till beyond
We'll
8, I'm
figure it
sure.
out.